Welcome to EDU World Space.
So, to answer the first part of the question, an electric field at point P, which is a distance r from a point charge, can be defined by this equation. So the potential is equal to the Coulomb's constant times the charge and the distance between the charges. The distance between the center P to the point charge is the radius r here in this case. Here, Q is a charge of the point charge. The electric field at point P, which is a distance r from a spherical shell of radius capital R, is, so this is true when the distance to the point charge is greater than the distance or the radius of the spherical shell. Now, taking in the other scenario where the radius of the spherical shell is larger than the radius to the point charge, then the equation will start to look something like this over capital R. So this is for when the distance is less than the radius of the spherical shell. So this is because an electric field at a point inside a spherical shell is equal 0. So there is no electric field inside the shell and its potential is 0. This means that a point charge can be moved between points within the shell without performing any work. So in other words, the potential between 2 points is the same and its value is similar to the potential on the surface of the cell. So this is a similar result to the potential of a solid conductor of radius r and charge q. So I hope that helped you understand the difference. So now to answer part B, the potential acquired by a balloon when rubbed against the carpet is the same as this equation. So if you could just bring it down here over R. So if you rearrange the above equation to solve for Q, we can get that VR, sorry, let me just differentiate between the R's and the, so VR over K. So plugging in the potential, V equals negative 1200 from the question, the radius is equal to 15 centimeters, and the Coulomb constant in the above expression, we can get that. Hold on, let me actually just plug them in first so you get a visual of the numbers and how you should be plugging them in. So it's 1200 volts times the radius, which is 15 centimeters. So it's times 10 to the negative 2, since centimeters is to the negative 2 for standard units, and converting to meters, over Coulomb's constant, which is 9 times 10 to the power 9. So this, when you compute this in your calculator, it's going to give you negative 20 nanocoulombs. And this is the final answer. So thank you for listening.